to attend this program. And if you have done so, I think you may want to, raise some complaints regarding that, because this program is absolutely free, and the lineup of speakers are spectacular. I will come to that a little later. Uh, but beware of people who might take mileage out of this program that we are running purely as a pedagogical activity from the hub. So I'm going to put it in presentation mode. I hope this is clear, Ram. Um, so
Yes, sir. Yes,
yeah.
Professor.
So what I will do is I'll give a brief introduction, and then Professor Dr. Ram Shankar, right, will give you a little bit of insight into this particular program that you are all registered for, right? So details and some logistics about the program, right? So the computing. Sorry, just a sec. Yeah. So the National Quantum Mission, right, program was launched in 2024, right? And the whole idea of this program is to create technology-driven programs in the country, right? And there are 4 hubs that are designated to take this initiative forward. Quantum computing hub that is located here in IISc Bangalore, quantum sensing and metrology at IIT Bombay. Then we have quantum communication hub that is located in IIT Madras, and then quantum materials and devices located in IIT Delhi. So these are all our mandates, right? And I'll be very specific about quantum computing in the next couple of slides, right? So the whole idea of the NQM, right, the National Quantum Mission, is to develop technologies, right? And technology through consortia, right? So what you see here, are different institutes across the country, right? All these institutes are partners in this whole technology development. And you see the green dots here. So these are all the hubs. So there are 4 hubs: Madras, Bangalore, Bombay, and Delhi, right? And then there are some lead institutes. So I'll tell you what these lead institutes are. So there are few lead institutes that you will see, and also there are member institutes. As I mentioned, this whole program runs as a consortium, right, in developing technology. It's not anymore one faculty member or one researcher sitting in one institute. This is truly a national initiative and also a collaborative initiative, right? You will see and appreciate, how this program is evolving. So there are around 43 institutes that are participating and 152 researchers across 17 plus 2 states and union territories, right? So there are 14 technical groups, right? And there are 17 projects that are funded, right, as the primary technical groups that's going to drive these 4 different technologies, verticals. So what is our vision from the technology or technical hub, right, from IISc? So we will concentrate primarily on quantum computing. So we want to enable a scalable quantum computing system, right? This is very important. Scalable quantum computing, what does that mean, right? So what that means is we can demonstrate a simple quantum computing experiment in lab. So we don't want to stop there. We want to build on top of that, demonstration and scale it to a level that it becomes a useful system. And we want this system to be indigenous, right? We don't want to buy things from outside because, as you all know, quantum technology is highly strategic. Okay, so both for computing and also for security purposes, right? So we want this to be indigenously developed, and also we want to develop all the infrastructure, the required infrastructure also be located within the country. And it is important that, we need human resource to run this, right? People to run this. So, if you are an undergrad student, postgrad student, or, you are a researcher, the future is very bright, right? So we want to make sure that all of you get engaged in this national mission. So this particular familiarization workshop is in that direction. Some of you may have taken some courses, some of you may not. So the whole idea here is to get yourself familiarized with all this quantum technology jargons and fundamental ideas. It will not make you expert, but it will be an icebreaker, right, for you to get interested and take up, a serious education or learning in quantum technologies. So we want to develop highly skilled human resource in the country, and also we want to be globally competitive, right? So when you have the infrastructure, when you have the human resource, I don't see a reason why we can't be globally competitive, right? So that is the whole mission of our hub, right? And we are located in IIC Bangalore, so this is where our office is, right? And if you are around IIC Bangalore, you're welcome to visit, right? So when you look at quantum computing system, right? So we go from physical layer to application layer, right? When we talk about physical layer, this handles material fabrication technology, interconnects, and everything, right? Similar to what you have for the classical computing, all right? But then you start to build layers on top of each other in order to make useful abstraction, right? So on the application layer lies the topmost, interface with us, right? So where you are going to run all your user-defined programs, user-defined problems that you're going to input, all right? So as a technology, we want to develop this whole vertical, right? This includes software, hardware, support system, right? When I say, support systems, it includes, even the simplest of the tools and equipments that we need to build a quantum computer. So, as a part of this technology development initiatives, there are four technologies that the mission has identified as an initial technical groups. You can see there are two photonics technical groups, two semiconductor technology groups, and then one superconductor technology group, and one ion and neutral atom technology group. All right. So, you may be wondering what these technology groups are and why these platforms are. That's exactly this familiarization workshop is going to, give you an insight. All right. So on the photonics, we have two semiconductor, two superconducting one, and then ion and neutral one. Let's just look at quickly, what are the mandates of this particular technical groups, right? So this is something that I lead from IISc, and you can see here, it's not just one institute. So there are multiple institutes spread across the country. We work together in order to develop a fully integrated photonic IC based, quantum processor, looking at 100 mode, boson sampling system, and also we are looking at, packaged devices as well. All right. So this could be used for many applications, and also we are looking at a fully integrated packaged quantum computing system based on photons. Right. And then this is Professor Chandrasekhar. He will also be involved in teaching the basics of quantum computing, and in his lab he's going to develop a 48 qubit system, right? And also develop some interesting architectures, right? That as a simulator here. This is again a collaborative project. And on the semiconducting side, right, so there is a 50 qubit semiconducting spin based quantum computer that Professor Abhishek from IIT Delhi is heading. This program is with Roorkee, Kanpur, Roper, and BITS Pilani. So again, you can see, a really a broad, spectrum of people and also institutions. And here he is developing cryo-electronics that will go in for, controlling semiconducting spin, particularly its silicon. And Professor Mahapatra from IIT Bombay, his technical group is looking at again silicon spin system, developing 50 qubit, quantum processor. And superconducting is again one of the mature technologies, and Professor Vijayaraghavan from TAFR, along with my colleagues here, Professor Vibhor, Professor Baladitya, and Professor Chetan from IISc Bangalore, are driving this program towards developing a 100 qubit quantum computer, and the technology will be used to develop a 1,000 qubit quantum computer. So the whole idea here is to develop a robust, an indigenous design to fabrication to packaging of these computers. Okay, so that is very important that I want to emphasize here. Though you might hear, a lot of, news about different qubit numbers from big companies. But what we are trying to do here is for long, long haul, interaction or rather development, where we want to have a technology that we should be able to scale up, starting from 24 qubits to 1,000 qubits, so that we don't rely on external foundries and ecosystem for delivering this. And then on the neutral and ion trap, we're looking at 400 qubits based on neutral atoms and then 50 qubit based ion trap system. And this is led by Professor Satyarishi Chaudhary from RRI, along with colleagues from IISer Pune, Roorkee, Guwahati, Kanpur, Patna, and IISer Bhubaneswar. So again, as I mentioned, this is a truly a national initiative. So if we want to realize all of this, we need infrastructure. Okay, so the mission has already sanctioned, or rather approved, 720 crores to establish the central facilities, right? And IISc will be hosting micro nano fabrication, characterization, and packaging facility for superconducting and photonics technology, while IIT Bombay will house semiconducting platform fabrication facility. And this facility is expected to come out for use in about 24 months, right? So this is going to be a key, initiative in creating an ecosystem where academics, startups, and industries can develop indigenous quantum chips. And as a part of human resource development program from the hub, we develop, these workshops, to educate people and also run internship to support undergrad and also graduates, postgrads, to get into this area of quantum technology. And also we have a QC bridge program for, postdoctoral fellowships as well. So this is 25 and 26 we will initiate soon. So this is just to give you some idea about, the first cohort of all the internship that we have provided for, different students, and they go to different places of eminence. Okay. And postdoctoral fellowship as well. We're working on different technologies, right, from algorithms to ion traps to semiconductors, right? And coming back to the program for today, I don't want to take too much time. This is a fantastic list of speakers. I think it will be really difficult for anyone to put up such a program. We are very proud of this group of colleagues who are experts and have done seminal work in the field. And just to start with, whomever you are going to listen, I think Professor Apurva is here. He is a pioneer in the area of algorithms, and he has done some very interesting, or let's say foundational work, right, in creating algorithms and also creating framework for students and researchers to interact with the algorithms through various frameworks, right? And we have people who are hands-on, right? Experimental physicists and engineers are going to talk to you, from Vibhor Singh, who is looking at superconducting, ion trap, and also a neutral atom, both from Professor Umakant and from Professor Saptarishi, and then semiconducting from Professor Madhu, and then Professor Abhishek, right? And then there is very important, set of lectures from Professor Chandrasekhar, who will, talk about really foundation, right, basics of quantum computing circuits, and he will also talk about photonic qubit systems as well. All right. So, I hope all of you should be able to attend this, right? Because last time we had this, during daytime, right, during office hours and class hours, but based on a popular request, right, we pushed it between 6 to 7 or beyond 6. Okay, so there are few lectures that will go till 9. I think this is to accommodate maximum number of participation, right? We don't want to miss anyone. So make sure you attend all of this, right? I will stop here, and in the next 5 to 10 minutes, Dr. Ram Shankar will give a briefer on the program and some of these logistics. All right. Thank you.
Thank you, sir. Yeah. So good evening, all. Thank you. Yeah, we have an overwhelming response today. We have about 700 participants online. Okay. So these are some of the key points that needs to be noted down. Okay. Please type your queries in the Q&A window, which is that you see at the bottom panel. So, and immediately after the session, say at 8 o'clock, we'll be, after the end of the session, 8 o'clock, at 8 p.m., we'll be sending you the quiz link. So the quiz link, the window will be open only for 3 hours and it will expire by 11 p.m. It's been set automatically. So hence we request you to take the quiz immediately, and participation certificate will be issuing it only to the candidates whoever have attempted all the quizzes. Will not be sharing any of the PPTs or the lecture recordings. So please avoid, the reaction button. I see a lot of reactions coming up. Please avoid that also, so that it will be disturbing for the other participants. So we'll move on to the next lecture by Professor, the first lecture by Professor Apurva Patel. Professor Apurva.
Okay, you can hear me?
Yes, Professor. Yes, Professor.
Okay, so now I will try sharing my screen.
Sure, sir.
Okay, you can see my screen?
Yes, Professor.
How do I magnify it? Or this is as large as it can be. Okay, fine.
Fine, Professor. Good to go.
Yeah. Now, how do I change the back and forth?
back and forth. I think you'll have to use the arrow keys or page down.
No, it's not working with the arrow.
Page down.
Well,
Page up, page down.
Okay, I will change it in my window and probably that will work. Let me see if it works here. Okay, it works there. Fine. So let me begin.
Thank you, Professor. Please go ahead.
Yeah, I'm talking about first quantum physics and then about algorithms. The whole reason for emphasizing the role of physics is that what we call quantum advantage very strongly depends on certain features of quantum physics. And we need to understand that, because unless there is sufficient advantage, we will not jump to quantum technology and put aside the classical technology which we already have. This is important for a very specific reason. There is a lot of hype in the subject, particularly in the media. It has arisen because of quantum potentialities. What is possible or what may be possible. But equally important part is quantum limitations. There are very strong limitations, and unfortunately, they are not being given due attention. And as a result, there is a lot of unnecessary hype, and I am going to try to cut down that hype. You will also listen to many statements from various other people, including in this course, and you should question them if you find that they are exaggerating something. So let me begin with the first fact. The first fact is the quantum advantage is problem dependent. Some problems are easy, but also some problems are hard. And there are acronyms for both these types of problems, BQP and QMA, which are given according to what computer scientists label as complexity classes. And why does this problem dependence arise? For that, you have to go back to the origin of quantum theory. It was invented to explain certain physical phenomena that existing classical theories failed to explain. Important characterization is failed. It was not that the proof in the classical theory was very long and you wanted to find a shortcut and you invented a different language. Not at all. Classical theory was just not capable to explain certain things. And what we call quantum advantage, it can be sizable only when such non-classical features are at the heart of the problems to be solved. There are many problems, whole of classical physics as a matter of fact, with different strategies to solve many problems. They include linear algebra, They even include Hilbert spaces or constructions for various kind of states. As a matter of fact, both linear algebra and Hilbert spaces are older than quantum theory. And if you believe that by just sticking to them, you will get some quantum physics giving you some new behavior or new advantage, you are mistaken. New features must come in. And one of the central features of quantum theory is Planck's constant. Planck introduced a new constant of nature. It did not exist in classical theory. And this new constant of nature was absolutely necessary to describe the quantum phenomena that classical theory could not explain. So to understand quantum potentialities, you have to ask, is Planck's constant going to play some role in the problem I'm going to solve? If it is not, then there will be some classical version, maybe known, maybe unknown, which will handle that problem. And you will not get any quantum advantage in tackling those problems. The second fact, we know that quantum dynamics is highly fragile against external disturbances. So it can work well in cooperative and protective settings, but not in hostile environment. And so you need to shield quantum dynamics from all the unwanted disturbances coming from the environment. And the environment actually includes the control systems as well as the measuring apparatus. The need to create this whole structure makes quantum technology expensive. And yes, quantum devices will get cheaper, but they will never get cheaper than the classical devices which you already have. Classical devices will also get cheaper, but the inequality will remain. And so it brings in a question of economics. Are you going to use expensive technology for solving certain problems? Well, you will do that only if the advantage is large enough. Important qualification, large enough. If the advantage is not large, you will make do with whatever we already have. It's common experience in our life. The third thing, which also is worth paying attention to, is that classical technology is not idle. It continues to improve. An interesting point is that some of these improvements are because of the competition with quantum technology. You are asking new questions from new ways of thinking, and that has been of help in improving classical technology. This kind of interplay tells you that what has been labeled as quantum advantage is a moving target. Both classical technology and quantum technology will be different 5 years from now than what they are today. And the benefit of the quantum, this competition is that there are ideas which we are labeling now as quantum inspired. Certain kind of quantum logic which we consider interesting is getting incorporated into classical devices. And that is also a very important development. What is the implication of this whole business? Well, quantum technology will be attractive only in cases where the advantage offered by it is sufficiently large to offset its cost. What are the situations in which such things will arise? And we can confidently say that this will be realized in special purpose devices which are actually customized subroutines in large applications. Lots of the peripherals and surrounding part will remain classical. There will be small quantum modules embedded in that, which will do specific quantum tasks which can be executed well. And this hybrid system is what will be the future of the developments in quantum technology everywhere. We need this for another reason, that we ourselves live at a classical level. We cannot directly understand quantum signals. Our questions are classical, the answers which we look are classical, and we have to convert back and forth. That also requires a hybrid setup. This whole background is what I'm going to expand by giving specific examples in the remaining part of the lecture. But before I do that, let me specify what to expect as far as practical applications are concerned. And here I have given 4 topics labeled by the colors corresponding to traffic signal. The first applications which are already happening are actually in sensing and metrology. They are exactly the small quantum modules embedded in large classical peripherals which I mentioned, and they will bring a lot of benefits which are not just limited to scientific domain, but also useful in public domain. The next one with the orange light are applications in simulations of physical systems. By physical systems, I mean physical systems in the quantum domain, and in communications, not in the sense of security, but in the sense of improving signal to noise ratio. And that can also have a lot of applications much beyond just the scientific domain. What comes later is a feedback of technological developments onto fundamental science, that by measuring everything more precisely and characterizing them with higher accuracy, we learn something more about quantum theory. What is it? We may not know today, but this is always the interplay between science and technology. Technology throws up new observations, and then science has to invent new theories to explain them. The computation, which is heavily advertised, is actually the last topic on the list. It's going to take some time, and it's not very clear in what sense and in what problems it will be useful. There might be something totally different in terms of applications which we don't even imagine right now. What is our status? Not just in India, but worldwide. That the theory is far ahead of practical implementation. And that is actually responsible for jumping the gun, saying that we can do this, we can do that, etc., but giving no idea about how difficult or how long it will take to reach those goals. There are constraints, both in terms of infrastructure, the hardware platforms, and manpower, the software and the logic which are necessary to building this subject. And we have to learn how to concentrate our resources, both in terms of infrastructure and manpower, to essentially build from scratch. And that is where it is useful to understand which are the specific areas where we'll get advantage and where we can contribute with our existing strength and limitations. We have to keep track of whatever goes around in the world, because we can learn from their mistakes. We can even reverse engineer certain things. But ultimately, we have to have indigenous development. There is no shortcut for that if you want to stand on our own feet. Okay, so now let me go to quantum physics from this overview. And I'm going to first use a language which is present in high school physics these days. That quantum physics involves both wave and particle aspects. Why it is so? Well, there is no better way to put it than what Feynman said. Nature isn't classical, damn it. It is what it is, and we have to try to understand what we find. And that's where we can make certain observations, that quantum objects simultaneously have wave as well as particle properties. It is not one or the other. It is not sometimes wave and sometimes particle, but it is simultaneously both wave and particle. And quantum dynamics evolves both wave and particle properties of the physical components. we need to find a language that can describe it and then try to understand the consequences. So here are the common representations of wave and particle that we use for encoding quantum data. I have labeled them as zero dimension and one dimension structures. Zero dimension is the notion of superposition, and one dimensional structure is a notion of ordered sequence of components. Mathematically, it is called a tensor product. If you don't know the words, ignore them. But why I have called them zero and one dimension is very easy to understand. Superposition refers to the situation where we have multiple signals at the same point in space and time. Important point is same point in space and time. A point is a zero-dimensional structure, and superposition puts both of them together, space and time, and it can be described in the language of a zero-dimensional algebra. Particles form discrete objects, which we can call letters of an alphabet. We arrange them in some particular manner, which is a sequence, and that one-dimensional sequential arrangement produces many different things, including what we call a register made up of certain bits in a computer. And this is sufficient to understand how waves can contribute to the algorithms, how particles can contribute to the algorithm. It's true that one can think about higher dimensional structures, but right now I will put that aside. What we need to understand that classical algorithms can use either wave properties or particle properties. And we can ask that if I have only wave properties, what all can I do? If I have only particle properties, what all can I do? And then I can extend to put both of these things together and see what happens. And that is what I'm going to explain next. There are many technical words associated with this language. One of them is called entanglement, another one is called coherence, but right now they don't matter. Just think of superposition and sequences. Okay, so let me begin with particles nature because it is quite familiar to us. We can construct various kind of sequences, and then what we realize that breaking up the information into a sequences of letters can actually reduce the resource requirement exponentially. And the best way to do that is go through simple examples. We are using a digital language, whether it is our number system or our written languages or spoken languages, but number system is easier to grasp. It uses a certain number of digits arranged in some manner, and the manner of arrangement follows what is called a place value system. It's an ordered sequence. It's just not a random collection. And easily we can identify how many digits do I require to cover a certain number of possibilities. For the number, well, you can say that I can use 3 decimal numbers and describe all the values going from 0 to 999. What is the relation? Well, there are 1000 values and you are using 3 digits. The 3 is actually log of 1000 to the base 10. Another example. How do you look up a word in a dictionary? Well, we don't look for a whole word. You break it down. That breaking down is a factorization process. First you look at for the first letter, then you look for the second letter till you reach the last one and then you have an answer. This process in a Boolean manner is called a binary tree search. How many steps you should take in the search? Where it is logarithm to the base 2 of the size of the dictionary. Every time you look up a letter, you will know that the correct target is either before or after it, and you keep on going till you reach the target. Fine, these are simple familiar examples, and now I can jump directly to the most general possible, which can be possible output which can be produced by a classical Boolean computer. The Boolean variables, which I have called xi here, have a nice property that xi square is equal to xi. There are only 2 values, 0 and 1, for each xi. So you can write down the most general output of a Boolean function as a multivariable system. It is actually a polynomial which is linear in each individual variable. And I have written down the general expression starting from the constant term, which does not have any variable at all, then the linear one, and you can keep on going to the largest degree, which is the product of all the variables. How many terms are there in this expansion? Well, it is 2 to the power small n. And you can easily count by summing the binomial coefficients, or more trivially by just realizing that each term can be labeled by saying a particular xi occurs in that term or it does not occur. There are 2 possibilities and variables. Total choice is 2 to the power n. And yes, these coefficients a0, ai, etc., which I have listed, they contain the properties of that particular function. For different functions, these coefficients are going to be different. So if you want to evaluate this polynomial, well, you have to evaluate all the coefficients, and there are 2 to the power small n of them. What can happen if you get lucky? And this is the best situation that can occur, that this polynomial can factorize. The maximum factorized form is where each variable appears in only one factor. I repeat, this is possible for certain types of functions only. But if it happens, then you can ask, what is the amount of effort required to calculate this product of factors? Well, it is small n number of additions and small n number of multiplication. And so the effort has been reduced to order small n. Where is the advantage? Well, the advantage is in the amount of time taken to evaluate this function. You keep on adding one by one in the original form, or you just multiply the factors in the reduced form. This is a advantage in temporal resources. The factor can be written as capital N divided by log of the capital N to the base 2. And this is the maximum gain achievable in particle-like implementation. It's an exponential factor if you write it in terms of small n, but you cannot do anything more than that. And that is what our classical digital computers do whenever possible. Take advantage of factorization. Now let me go to superposition. As I said, it allows you to have multiple signals coexisting at a single space-time point. And that gives a scenario which is known in the computer science language as a single instruction multiple data task. That all the signals which are superposed can be handled together by a single instruction, which transforms all the components at the same time. It turns out that that can reduce the resources. That reduction is also exponential, but this reduction actually is in space. There are parallel threads which are commonly used in our parallel computers, but if you can superpose all those signals, you will reduce the hardware of parallel computers and bring everything down to a single processor. Best thing is to again go to examples. Wave broadcasts are very common in communications. Just look at our mobile phones. There is a signal transmitted from the broadcast tower. The broadcast tower does not transmit signals for one user and then another user and then another user, etc. It broadcasts signals for all the users in one shot, a superposition. It is left to the user to pick out the interesting signal corresponding to his or her own device, and that is what the mobile phones do. It will pick out one component from this huge superposition of signals. And so how much does the broadcast tower achieve in terms of advantage? Where it is just the number of superposed signals. And you can ask now how many signals I can superpose and what will be the effort required to do that. And here I have again given the best possible answer. I have written it in the quantum notation, but it is the same in any vector space language. That you consider a binary signal of 0 and 1. And if you rotate it by 45 degrees, which is possible in the wave language, you can have a superposition 0 plus 1 by root 2. And this requires only rotation on the n different modes, the small n different modes, each rotated by some amount, and the result is a uniform superposition. If you expand out this product, you will get sequences of all 0 and 1 occurring in some order or the other. And how many terms are there in the uniform superposition? Well, it is 2 to the power small n. So what the broadcast tower can do, it can use this small n number of effort to superpose 2 to the power small n number of components. And the difference between the two is again the exponential capital N divided by log n to the base 2. And this is the maximum gain achievable in wave-like implementation. It's very interesting that this n by log 2n, which appeared in the wave language, is exactly the same as what appeared in the particle language. And there is no simple explanation for that, but it tells you that there are two factors of exponentials available in these two different languages, and it's up to you how you can combine and extract both of them. There is a caveat whenever dealing with superposition, which I must emphasize, that the user cannot look at all the superposed components simultaneously. As I said, you will pull out the one signal which corresponds to your mobile device. And there are small n number of different modes which will allow you to superpose 2 to the power n components. But at the end, you can extract only small n number of selected properties. How you extract it up to you. You can have interference, amplification, whatever else. But this is a limitation every time you use superposition. Okay, so now let us try to put them together. Classical algorithms can use either factorization or superposition. Quantum algorithms can use both of them simultaneously during the execution, but with a caveat that the final result will reduce to classical results. And so we can say both strategies can be exploited the best where the gain of factorization and superposition do not overlap. If they overlap, then there will be trade-off, and I will give examples of both these types. On top of that, we need that the output has to be concentrated in a few wave modes to get around the restriction that you cannot observe all the superposed components. The best situation is just one mode, which is known as the delta function. That is fine. If we have a problem of this particular property, well, we'll get best of both the worlds. And this is a feature which explicitly will illustrate that quantum advantage is going to be problem dependent. How you can exploit these features and which are the problems in which you can do that. I will take a little bit excursion to point out something which I mentioned earlier, that there are so-called quantum-inspired algorithms. They don't use quantum dynamics, but they use what is known as coherent dynamics from a wave source. A wave source can have in its signal both magnitude and the phase information. And if we can somehow track both magnitude and phase information, you will have a solution to the problem which will mimic the quantum principles, and where you will say that even a classical strategy can do something useful. And the best example for this is actually from our own experience, that we have 2 eyes and 2 ears. They are both wave detectors. And the 2 eyes and 2 ears do something which 1 eye and 1 ear cannot do. The eyes, by combining the two signals, which will be a spatial shift from a common light source, it allows you to combine magnitude and phase. How it is done inside our brain, we still don't understand, but we know it happens. And that is a judgment of parallax, which is something which I could not have obtained with 1 eye. 2 ears again do something similar inside our brain. The difference now is in the time instead of space, as in case of eyes. But that little temporal difference gives a signal detected in the 2 ears, slightly different arrival time. And by measuring that difference in the arrival time, we can judge the direction of the sound source. And this is a novelty. Well, 1 year just could not have done it. And you have to keep in mind that yes, these are the kind of situations, they are called quantum inspired algorithms. We have not used them very much for the simple reasons that we have not thought about it. Result is our historical development of computation. Something got left behind, but if you are smart enough, well, you will pick up these missing threads. Okay, so now let me go to the examples of this wave and particle combination. So the first example is the algorithm which made the subject of quantum computation famous. It was an algorithm discovered by Peter Shor, and it implements Fourier transform. Fourier transform is nothing but a change of basis from some set of variable x to the conjugate variables y. And it's implemented by adding up all the components with a phase factor. And I have written the phase factor in a discrete language, which is what is used in a digital computer. There are n components, and x and y are the two coordinates. One transform from x to y. The 2 pi I in the exponent is factored out, so x, y, and capital N are all integers, and the integer part does not contribute to the phase, only the fractional part contributes. And this operation can be very easily implemented as a factorized process. One have to arrange things a little bit, but all we are interested in is the fractional part of xy divided by n. And you can write both an x and y in a binary notation. Each bit will follow the place value system, and there are various powers to arrange with it. And you can then multiply the two and see that, say what is the coefficient of y subscript n minus 1, which appears in the fraction. Well, it is only the last bit. If the next bit is that x1 by 2, well, y n minus 1 came with a power of 2 to the power n minus 1, multiply by 2, it will become 2 raised to n. 2 raised to n does not contribute to the fraction power, it will become 2 raised to n divided by capital N. It's an integer, it does not contribute to the phase. And now if you rewrite this structure, notice that it is linear in each variable y. So the transformation from x to y written as this sum over y with a particular phase, it completely factorizes. Y is linear, it is in the exponent, well, you just separate out all the terms and you get a product. And there are capital N number of terms in this matrix, that is the dimension of the matrix. Well, you can write it as product of small n number of factors. It's very simple, and this is a particle-like implementation which I mentioned earlier, and this is what a quantum Fourier transform will do. And even though I described everything in a quantum language, there is nothing specifically quantum about it. This is exactly what the fast Fourier transform does in our digital computers. The gain for doing that is capital N divided by log n to the base 2. So Schur did not just do that. Otherwise, he would have just repeated the fast Fourier transform. He did something more. And that something more was finding what is called the periodicity of a function. And it's a little exercise in number theory, which says that if I have a periodic function, fx is equal to a to the power x, periodicity comes from this modulo and arithmetic. If I can find the periodicity, then I can factor this number. I will not go into the details. It is well known in literature, and you will find many illustrations for it. But the important point is that when you try to evaluate a Fourier transform of a periodic function, you will obtain a delta function. The location of the delta function is exactly the periodicity of the function f of x. What do you have to do that? Well, evaluate this function value of x with all of x values in parallel. In the wave language, it means all of the x values are superposed. And then the result is that the final superposed components will nicely interfere in a manner that you are left with a delta function. This is something which is again well known in signal processing. We just Fourier transform a periodic function to find its frequency. And so period finding now does a peculiar combination. There are two variables x and y, but now I am going to run all the x values in a single run of quantum Fourier transform, and the y part I already saw that it was completely factorized by the fast Fourier transform. So I get this factor n by log 2n twice. And this is what happens in Schur's algorithm. Both the gains reach their maximal values, and the complexity for period finding problem reduces from order n square to order log 2 n square. There were two factors of n, both of them got independently improved. And surprisingly, Shor discovered this algorithm which is best of both worlds. And the first algorithm actually gives the best scenario about what a quantum computer can achieve. No quantum computer can do more than that. Now let me go to Grover's algorithm, which refers to factorized search in the particle language. The problem is actually something called as a database search. It's a relativized problem where you are searching for a particular item in a large collection of objects, but you are given a specific binary oracle. Oracle just means that it allows you to identify the object, whether it is the one which is of interest or not. And if you are given just the random structure, well, you cannot do anything better than picking up the items one by one and checking whether it's the right one or wrong. But we don't do that in practice. In practice, we break up this oracle into smaller parts. I gave the example of looking up a word in a dictionary. You look at the word letter by letter. If I do that, and the generic situation is a binary search tree, that you can get the maximal advantage from factorization, which happens to be going from this capital N to the log n to the base 2. Now comes the question, what can I do more with the wave dynamics? There was only one factor of n, and the particle factorization already took care of it. So the only one amount that is left is a little bit, that the number of queries is this particular number, and I can ask, can wave dynamics allow me to identify certain number of objects with one binary query? And surprisingly, the answer is yes, it can do better than the binary or the Boolean structure. And the answer is that wave dynamics can uniquely identify 4 objects by a single binary query. And so it gives an advantage, which is a factor of 2. It's not exponential, but it is still something. And the best way to answer this is give a pictorial illustration, which I have done in this particular figure. Remember, you are going to use a single binary oracle call, and you are going to identify 1 out of 4 objects with certainty. So this is waves. So we start with amplitudes, not with bits. The initial state is unbiased. All 4 amplitudes which are superposed in some sense are equal, unbiased, uniform distribution. Then you can ask a binary question. And here, wave dynamics offers something which is different, that I can use the binary question to flip the sign of the amplitude. If it is positive amplitude, I can make it negative. Waves oscillate, and so this is something which can be done. And what do I do afterwards? Well, just wait. How long? Well, half a period of oscillation. This binary oracle question is like throwing a stone in a pond of water. It creates a disturbance. And the waves then oscillate about the average value. If you calculate the average value of 3 plus half and 1 minus half, it is a quarter. And if you wait for half of oscillation, then all the ones which are plus half get reflected on the other side of the average to 0. And one which is minus half gets reflected into a quarter onto the other side, it becomes 1. And that's the place where you say, stop the algorithm and look at the signal. Well, all the signal is in the target object, which responded to flipping of the sign of the wave amplitude. Here I have taken it to be the first object in the list, but it could be anywhere. And this is a factor of 2 advantage. Nothing sophisticated is used, only simple reflection properties of waves. And this is what Grover discovered. And it is a non-trivial result. Now you can ask here, something is achievable, and can I play around with these ideas a little bit more? This one actually has a lot of applications in different areas, but I will not go directly at that. Let me address a combination of wave and particle aspect first. So what Grover showed is actually applied this algorithm not just to 4 objects, he applied it to n different objects and demonstrated that the maximum gain you can achieve by superposition actually is square root of n. It is not the maximal value of n by log 2n. And this algorithm actually is so simple that it can be implemented just by coherent wave modes. The important part is that it saves in the time complexity. This reduction of the waves is in time complexity, while this factorization part doesn't contribute to the Grover's algorithm, and space complexity will be remaining. As I said, I will skip the application part right now, but let me now look at the result. What is the maximum you can do? And that number happens to be this n by log 2n by factorization of the queries, the letters in the alphabet of binary search, and an additional factor of 2, which came from this identification of 4 objects by 1 binary query. I can look at it in 2 different ways. The one which I've described is first factorization and then superposition. That's the first line. But I can do it in the opposite order. First, I apply superposition, which takes me n to square root of n. And then I apply factorization onto this square root of n queries. It will give root n divided by log of root n to the base 2. And you realize that both these numbers are the same because log of root n is half of log n. So yes, this is the maximum gain in Grover's algorithm best that a computer can do. You can understand it by arranging the factorization and superposition in different ways. But the point is that the algorithm is having an overlap between how much a factorization can do and how much a superposition can do. And so you are not getting best of both the worlds. Fine. There is another well-known algorithm which actually is easy to understand by just power counting. And that is the algorithm of quantum walks. In classical physics, random walks are diffusion processes described by this equation where the time derivative of a function is given by the Laplacian of the function. It is called a diffusion operator because Laplacian does exactly the job of spreading out the function in its neighborhood. And it has a very simple scaling, which is obtained by just looking at the powers of time on one side and the powers of space on the other side. Two powers of space in the Laplacian, one power of time in the derivative, and that produces what is known as a Brownian motion signature. Distance, which is the position, proportional to square root of time. What happens in case of waves? Well, waves follow a different equation. Second derivative of the function is proportional to its Laplacian. And if you now count again the powers of time and space, well, it gives distance is proportional to time. We know that from our experience. You throw a stone in the pond and the wave emerges, it travels outside at a constant speed. So actually you can explore the space faster by a wave than by a random walk. And this can be built in quantum algorithms. It happens that the best language to do this is use a special relativity. I don't want to go into the detail of it, but it describes modes where distance is proportional to time. That is a signature of either waves or relativity. And you can look at it in both the languages. The consequence of all this is again a speed up, which is governed by the square root change. And combining Grover's algorithm on one hand and this quantum walk on the other hand gives you a strong result that any NP complete problem can be speeded up at least quadratically. Quadratically means that effort can be made into a square root. This is a generic result. The factor can be small, as I mentioned, going from 4 to 2 in case of the database search, or it can be going from say 1,000,000 to 1,000, which sounds much better because the numbers involved are larger. But this can always be achieved. And if you are clever enough with quantum inspired algorithm, this is the gain which you should look for. Okay, now let me go to quantum physics. And here I will mention things which you may not have encountered too much in the first course on quantum mechanics. But these are well-known facts many of them going back to more than 50 years or even sometimes to the origin of the quantum theory. And the first different point other than this wave and particle which appears is the concept of density matrix. Now the density matrix is a most general description of a quantum state that you can have. And in the reverse, you can also say that each and every component of quantum density matrix can be measured. So there is a one-to-one mapping between quantum properties of a state and labels in the density matrix. It has certain nice properties which I have mentioned. It is a Hermitian matrix denoted by rho dagger equal to rho. Rho is my notation for the density matrix. It is positive, that means all its eigenvalues are between 0 and 1. And the upper limit 1 is constrained by this rule that trace of rho is equal to 1. So all the eigenvalues add up to 1. And so it has a nice description in terms of a probabilistic labeling of the eigenvalues. What is different? That a density matrix is actually a generalization of the concept of probability distribution to quantum theory. And this feature comes from the fact that it is actually a matrix which will have both diagonal elements and off-diagonal elements. The diagonal elements can be identified with the eigenvalues that have a nice connection with the probability distribution. But what about the off-diagonal elements? And they carry something which is unique to quantum physics. They encode what is known as a symplectic structure. This is a technical label, but it is an association between the variables describing a theory by breaking them up into canonically conjugate pairs. And the most common thing which we know as an example of this is a position and momentum. In one-dimensional system, given a position and momentum, I can use Newton's equations or Hamilton's equations to describe the trajectory of how the particle moves. But when you go to quantum physics, well, the position and momentum become operators, they don't commute. And this non-commuting part is the important signature of quantum physics. The commutator of x and p is equal to I times h cross. The Planck's constant explicitly appears. And that is the signature of quantum physics, which is buried in the definition of this density matrix, particularly its off-diagonal elements. There is another version for those who are familiar with qubit. The state is described by a surface of a Bloch sphere, and you have two coordinates on the surface, theta and phi, and you can write them as conjugate pairs, as cosine theta as one variable, phi is another variable, and the product of those two gives the elemental area on the surface, sine theta, d phi. Okay, so what happens to this density matrix? Well, you can write its evolution in the Schrodinger picture very easily. It is governed by this commutator of what is called the Hamiltonian and the density matrix with an explicit appearance of the Planck's constant. What is the general result for the density matrix and its element? That if you take a pure state in an n-dimensional Hilbert space, n-dimensional pure state is described by n-component complex vector. Then its density matrix has 2n minus 2 real parameters. Complex numbers has 2 real components. So n complex vectors will become 2n real numbers. But then I'm subtracting of 2. One of the 2 is just a normalization. Trace of the density matrix is 1. But the other minus 1 comes from the fact that overall phase of a quantum phase is unobservable. You can measure all the relative phases between different components, but you cannot measure the overall phase. And this is again a technical label. The density matrix describes what is called a ray in the Hilbert space. Putting both these things together, you have 2n minus 2 real parameters. And then there is a general theorem which shows that these 2n minus 2 parameters are actually n minus 1 canonically conjugate pairs of variables, just like position and momentum was one pair. If I look in 3 dimension, I will have x1, x2, x3, p1, p2, p3, and I will have 3 pairs of canonically conjugate variables, x1, p1, x2, p2, and x3, p3. And the same thing works for density matrix, and you will have n minus 1 pairs. And all these n minus 1 pairs, as in case of position and momenta, will obey this uncertainty relation that you can measure one but not the other at the same time. So you can measure n minus 1 parameters of the density matrix simultaneously. So this is a mathematical structure. It's important to point it out even though you may not understand all the mathematics which is there, but it allows you to say that I want to get an advantage. I must play around with all these canonical conjugate pairs as much as possible. And the punchline is that quantum advantage is impossible unless features of density matrices which are not present in classical probability distributions are exploited. If you are not going to exploit the peculiarity of the quantum density matrix, you are not going to get any quantum advantage. So now let me come back to the fundamentals which I have described, but I will now summarize them in a single slide. The first object which I mentioned was Planck's constant. Where, what all places does it appear? So we know that it quantifies the commutator of canonically conjugate pair of variables. Position, momenta, commutator gives you I times h bar. And from this you can progress to the uncertainty relation, which says delta x times delta p is bounded from below by half of h bar. It also happens to be what is known as a minimal elemental area in the phase space, that the small volume associated with one particular quantum state is a Planck's constant, and this feature will be obvious to those who have learned a little bit of quantum statistics, that if you either describe Bose-Einstein or Fermi-Dirac distributions, you actually end up counting the number of states. And the number of states you count as the total volume in the phase space, d cube x times d cube p in 3 dimension. But then you put a factor 1 over h cube in front. That 1 over h cube in front is the minimal elemental area. It's intimately tied to this uncertainty relation or the commutator between position and momentum. And it is part of the description of phase space. Planck's constant also happens to be the unit of angular momentum. Position times momentum gives you a dimension of angular momentum. Most of the time, the angular momentum in textbooks is written as values 0, half, 1, 3 half, 2, etc. All the numbers spaced by half integers, but this h bar is implicitly present. It is just omitted for the sake of convenience, but it is there. It is also the quantum scale for action. For those who have dealt a little bit with Feynman's path integral, they'll realize that the phase factor which appears is e to the power I times action divided by h cross. And it also governs the magnitudes of energy quanta and spacing by the fundamental relation that E is equal to h times nu. If you have 1 photon, 2 photon, 3 photon, etc. states, well, h nu is the spacing between all of them, and the discretization of the spacing inherently brings in the Planck's constant. So if you have quantum effects to look for, you have to identify that in the problem, this h is appearing somewhere or the other. Well, it appears in many different ways, and so you look for it. The second part I mentioned is density matrix. It has its peculiar off-diagonal elements. In there are complex elements. And these complex elements are responsible for describing interference phenomena. The diagonal elements of the density matrix are all positive numbers, and they cannot describe interference. To describe interference, I should have the possibility that something can add and something can also subtract. But that happens with these off-diagonal phases. How does it influence the calculation? Well, in any problem, you are going to ultimately measure some observable quantity, which you call expectation values in a probabilistic scenario. That expectation value is given by trace of density matrix times the operator. Density matrix and operator both are Hermitian objects in quantum physics, and they can be diagonalized individually, but when they commute, they can be diagonalized simultaneously also. And if that happens, then trace of rho times O just becomes the sum over diagonal elements, which can be described completely classically. You may not know the algorithm which will do that, but there will be an algorithm which will calculate this expectation value in a completely classical situation. And so non-classical features require that these two Hermitian objects, rho and O, do not commute. Only when they don't commute, there is a possibility of getting a quantum effect. What do you do next? Well, you want to maximize the quantum effect. And that can be done by taking the commutator of rho and O and choosing their orientations so the norm of the commutator is as large as possible. And in that particular situation, you can get the best signal which has a quantum character. And the examples of these are again well known. If you want to measure polarization, you put the filters perpendicular to the direction of polarization. Or if you want to measure a signal in NMR or nuclear spins, put the RF coils which measure the signal perpendicular to the background field. So this is again a well-known feature. I'm giving you the answer without going through all the detailed algebra. And there is one final property of the density matrix that I want to point out, that if you are clever enough, then you can make this density matrix real. But what will remain is that the real values are not necessarily probabilities. Sometimes those values will be represented as a negative weight, and to compensate for the negative weight, there will be some other configuration which will have weight that is larger than 1. What remains true is the sum of all the weights equal to 1. But the individual weights cannot be interpreted as probabilities. And this is the peculiarity of certain kind of quantum scenarios where the off-diagonal elements of density matrix are doing something non-trivial. In physics algorithms, this thing is referred to as a sign problem. It cannot be explained in terms of conventional probabilities. You have to have negative weights. So this is actually a one slide summary of all the features which are peculiar to quantum physics and which is what we should look for in designing good quantum algorithms. And now my last comment, and one have to keep in mind that the features which I all went through, they are necessary conditions. They are not sufficient conditions. And the best way to illustrate that is that you can have classical solutions in very simple cases, analytical solutions where Planck's constant is present. And because the solution is classical, well, we can explain quantum effects by classical logic. The best example, going back to the start of quantum theory, is the solution to the hydrogen atom problem. Here you have an analytic solution, quantum problem is solved. And this remains true of more general quantum problems also. The problem may not be solved now, but you cannot guarantee that there may not be a good analytic solution or good analytic approximation which some smart person will come up in future. And if that happens, that smart person would have solved a quantum problem in the classical language. So one can now emphasize various things which I mentioned as necessary conditions for improving quantum algorithms, though not necessarily sufficient ones. And the examples I can repeat: the off-diagonal elements of density matrix, a non-zero commutator between density matrix and the operator, weights which go outside the 0 or 1 interval, which happens in Wigner distributions and Feynman path integrals. There are dynamical correlations in evolution, which are consequences of interference and sometimes even consequences of identical particles. Note that identical particles is a strictly quantum feature. It has no analog in the classical physics. And there are also things which are called squeeze states. So these are all non-classical features which have to be present in some sense in a problem if you are looking for a quantum advantage. There's one of them must be there in some form or the other. And this actually gives very stringent constraints. One particular example I want to mention is machine learning. And there the statements translate to the quantum advantage is possible only when the input data have quantum properties. By quantum properties, I mean the input data must have both magnitude and phase information. It can be a density matrix with both diagonal and off-diagonal elements. You must use it so that the whole correlated stream of the input data is fed inside a quantum processor without any projective measurements in the middle. If you do a projective measurement in the middle, you will collapse all the quantum structure into a classical one, and then all the advantage of quantum physics will be lost. And unfortunately, most of the things people are going to try in machine learning these days is use classical data and a quantum processors. Well, nothing much is going to come out of that. What do you do? Well, you can ask for these parallel data streams, which are equivalent to actually multiple copies of a whole. And if you are allowed to do that, you can get exponential quantum advantage. Where the advantage is coming from? It is going to come from coherent correlations between parallel data streams. And how many parallel data streams do you need? Well, I can repeat the answer which I gave from biology. 2 parallel data streams are enough. 2 eyes and 2 ears can do something non-trivial, which a single eye or a single ear cannot do. This has been rigorously proved, and I have cited the reference here. But that is what one should look for. Can you collect quantum data? It may be from images, it may be from some experiment, it may be from some sensing device. If you can collect parallel data, well, there is a lot of things to be done in machine learning in that particular scenario and improve the signal to noise ratio. I think this is a good place for me to stop. Thank you very much. If you have some quick questions, you can certainly point it out by writing it in the chat box. But otherwise, there are references The good references are actually my own lecture notes and talks I have given at various places. They are all freely available from my webpage for anybody interested in more details.
Thank you, Professor.
Okay, Ram Shankar, I am done.
Yeah, thank you, Professor. So, will you be able to access the Q&A box, which is at the bottom? There are about 16 questions as of now.
Yeah, let me look at the questions which will be listed under what more?
Q&A.
Q&A, okay, fine.
Yeah. There's a button Q&A.
Okay.
If you can click on that, there are about 19 questions.
Okay, what does gain mean? Well, gain is as simple as whatever you understand in the colloquial language. You can do something better in one scenario versus another. Nothing more fancy than that. Are quantum computers available today sophisticated to enough advantage of Shor's algorithm? Answer is no, and it will be years before they can reach that. And the technology so far can do something much simpler. It can do these factors of two kind of stuff, which I illustrated with Grover's algorithm. Not much more than that. Brownian motion is slower. Of course, it is slower. If you want to go to a certain distance, it will take the time which is square of the same time required for a wave propagation. Nothing more complicated than that. You have to say that the distance is the same. Well, what is the time? One of them is the square of the other. There's nothing fancy about writing square root. If you don't like it, square the whole equation. The equation doesn't change in terms of its content. Algorithms certainly fit into a hybrid structure as a special purpose devices. As I said, the quantum component which will give you advantage will be targeted onto very specific problems. And the rest of the problem has to be tackled classically. And so it becomes a subroutine, which is a hybrid architecture, some part handled in a quantum component, some part handled in a classical one. What is the best encoding available for high dimensional structures? Where this requires a little bit of a geometry, but the structure happens to be something called a simplex. A simplex is the elementary volume in dimension d defined by d plus 1 points, so that none of these d plus 1 points are coplanar. If you try to discretize the space using a hypercube, then in d dimension you will require 2 to the power d points. That is exponentially large compared to this d plus 1 of a simplex. But to understand the geometry of a simplex, well, you have to do some homework. Quantum kernels can be used to map classical inputs into Hilbert space, but That doesn't save you anything because you have to encode the whole training data. And the training data does not map nicely into a quantum Hilbert space. You have to go through the whole training data. You cannot just say that I will keep a subset of it and ignore the other. There are all questions of that particular type. And then the quantum kernel happens to be useful only for problems which has underlying quantum structure. If there is a good classical structure in the data, classical kernels will do as well. Numerical stability is a different paradigm. This power counting does not deal with it. In real world, everything is truncated. And you have to have an arbitrary precision arithmetic if you really want to deal with numerical stability. In real world, everything is truncated, and to get stability there, you actually need control over errors. And controlling errors is another topic which I have not touched upon, but it can be again tackled by the same language which I have used. You can look up my lecture notes. The Baron-Plateau effect is actually a disease of the problem and not of the method. What is the kind of data you have? If you have quantum data, well, the Baron-Plateau does not appear. If you have classical data, it does. Model overfitting and underfitting. Well, it's actually a useless exercise that to fit a data set containing 10 digits, you have to use millions of parameters. If you are smart enough, you would have constructed something like a brain which will do it with far less number of parameters. So overfitting and underfitting are the problems of the machine learning algorithms. They are not problems of the underlying structure in the data. We don't have good machine learning algorithms. That's what it says. They are all brute force kind of algorithms, and that's why they have all problems. Gradient behavior and training, same reason. Algorithms are not good enough. Quantum kernel evaluation cost cannot be reduced if you are going to use classical data sets. And if you can reduce it, then there will be some classical version which you may not know, which will do the same job. Again, what do you mean by samples? Has to be converted by an extra label, whether it is classical sample or a quantum sample. Consequences are different for different things. Again, the strain stress split strategy does not apply for quantum algorithms. What applies are the strategies which I mentioned, 2 eyes and 2 ears, multiple point of view looking at the same data. It's very different than train and test. medical imaging, again, don't think of brute force encoding. Medical imaging has lots of features which you directly can convert into a quantum inspired language. Magnitude and phase. If you want an example, you get ECG. It's a fluctuating signal consisting of wave components. It can have magnitude, which you see on the paper by some graph. But where is the phase? And phase is completely ignored in all the ECG machines. It's there in the time sequence. It's an oscillatory signal, it has a phase, but no machine has made use of it. If you figure out a use for both magnitude and phase, you'll have a better ECG machine. Open challenge. I already gave my timeline about what is going to happen in the industry. Go and look back at the traffic signal scenario which I mentioned. Industry, most of the time, is focused on marketing. It's not very different from what a vendor on the street tries to sell you. They will sell whatever they have in their hand, and they will try to advertise it as well as they can. Whether what they have in hand is useful to the client or the user, that's an altogether different story. Companies can be far more sophisticated than the vendor on the street, but not very different. Well, tomography is expensive because we have non-commuting variables. You can't measure them simultaneously, and there is no way out of it unless you have problems where the answer is a delta function. Then measuring just one component is good enough. But as I said, the density matrix has lots of non-commuting variables. You have to figure out that variables which I want is in a small corner, then I can do a good job. If I want to measure everything, there is no shortcut. Non-zero Planck's constant is a new constant of nature, experimentally measurable, and something which does not exist in classical physics. It's a necessary condition for quantization, and that is all I said. Hybrid mode. I will go to the opposite extreme. All the quantum computing applications are going to be in the hybrid mode. Forget about QML because QML is something completely vague, even though there might be thousands of papers written on it. Parallel data stream is nothing but what you do on a parallel computer. You have something which is called a domain decomposition. You give different domain of the data to different processors to work on it. And they can be combined in superposition for certain class of problems. Okay, quantum physics knowledge, as I said, gives you necessary conditions, not sufficient ones. So you cannot use it to build quantum algorithms, but you can certainly say that which quantum algorithms claimed by people are useless. Physics calculation has no connection with languages. Languages are personal choices. You can use many different versions and many different libraries. It doesn't connect at all to the problem that you are trying to solve. There are many partial differential equations. You have to ask, they are equations of classical physics or quantum physics. And that will tell you whether there will be anything useful that quantum physics can contribute to it. You may not know the best classical answer, but that is a different story. Qubit transmission, well, you have to characterize what is a qubit. You have polarized light coming to us from galaxies far away. The polarization is a qubit. Distance is not the question. The carrier of the information is the question. People have tried all kinds of tricks from classical to quantum data conversion, but there is no shortcut that if you have n data points on the classical side, you will need n components. In the quantum data, there is no reduction. I have not much to say about Majorana 1, but I can certainly say that a quantum processor powered by topological qubits does not exist as of now, and it is questionable whether it will ever exist. Quantum computing engineers. Well, you have to learn quantum physics, no shortcut. Because, as I said, you can do all the linear algebra, you can do all calculations in vector spaces, but unless you learn quantum physics, you will not know whether the whole effort is worth anything. Mathematics. Well, mathematics is not physics. Physics concerns what is available in real world. Mathematically, you can construct a whole lot of different theories which may be self-consistent, but which has no physical realization. The only thing I can say about quantum materials relevant is they must produce a signal which reflects dynamics at the Planckian uh, scale, Planck constant scale, or the dynamics of the density matrix. If you can do that, then they will be quantum systems. Thermalization and information loss actually refer to non-closed systems, which I have not discussed. They are problems of open systems. They require more mathematical tools to handle, including error correction and non-equilibrium dynamics, but that is beyond the algorithmic part which I addressed today. Yes, there is problem with dealing with quantum systems of arbitrary sizes and at the same time controlling the individual components. The problem comes because you want to address each component. In hardware, you have to connect it with some wires or some electromagnetic signals by lasers and so on and so forth. And the density of all those structures just becomes too large beyond a certain size, and you cannot control it arbitrarily. And the answer is that you have to go for a modular design where there are individual components with certain communication. And this has nothing to do with quantum systems. We find these days it very much true in the classical digital computers also. They have kind of reached limits of how much can be done on a single processor. So now there are multiple cores and multiple threads and various parts of a system connected together with certain communication schemes, etc. It's a necessity. And the scales are different, but the feature is the same. Quantum education. Well, you have to start from the grounds up. You want to directly jump to a high level, you will miss out on many things and you don't know whether it is useful or not. Well, Shor's and Grover's algorithms were discovered now what? More than 30 years ago. And the fact that nothing much has been discovered in more than 30 years, despite a lot of smart people trying very hard, tells you something about the nature of quantum physics and where it can give advantage. It's rather restricted, and that is where the various struggles are. Yeah, Google recently launched this Willow chip and claimed a demonstration of observation of a quantum signal. if you look at all the details which have gone in, you will find the various features that I have mentioned in terms of conjugate variables, sign problem, encoding, etc. And that is how they narrowed down a particular signal to measure. But it is just a demonstration of a artificial problem at the moment. It will be a while before it can be connected to a useful application.
Yeah, Professor, sorry to interrupt.
I think I have reached the end of it.
Yeah. Thank
Time
you.
is also too much over
Yes,
the
yes.
limit. So
Yeah.
I will stop here.
Thank you, Professor. Thanks a lot. Thank you. Have a good day. So thank you all the participants. Let's see tomorrow at 6 p.m. Okay. Tomorrow we have 2 lectures scheduled during the same time, 6 to 8 p.m. So I'll be sharing the meeting link short tomorrow by before noon. And you have already received the quiz link also. Thank you. Thank you all. Good night.
Yes, thank you, Ram. Good night.
The recording has stopped.